Alright, today I'll talk about the problem, the perfect stall. So this problem seems complicated, but actually what you can do is use a maximum flow. It's basically the same as a maximum flow problem. So you give each stall a number, and then also give the cow a number and connect the cow to this stall, and then we just have to find the maximum flow for each of the stall. So here overall, if you know how to implement this, then the rest will just be using normal maximum flow problem. And so first, we'll get all the cows. So this is the ID for the cows, and we will set it all to the capacity from 0 to I. So we'll set this all to 1, and 0 is just a starting node. We can start at this node, and so then we'll be able to go down through every node, and finally we will end up at 405. So I just set this as the ending node because in total we have at most 200 cows and 200 stalls. So the ending, so every time when we keep track of the stalls, we will increase the stall number by 200. So this way we don't have overlaps with the cow number and the stall number. So here when we're reading the input, we have to increase the stall number by 200 and set the capacity to 1. This means that there's a path from this cow to this stall. And here I will set all of the stall to be connected to the final node. So then this way at the end we can compute the final flow, the final maximum flow of all of the stalls, and then we'll get it inside this node. So then we can print it out at the end. And so we set all of the stalls into this. We connect all the stalls to this 405. So we start at 201 because here we increased everything by 200. So normally we'll start at 1 here, but then we will. But here since we increased by 200, we'll set this to 201. And if we don't add 200, we will start at m. But now we have to add at 200, so this will also be 200 plus m. And we set all of those to connect it to the last node. And here we just use normal maximum flow. So I used a BFS for this problem. There's no need to find any optimal edge or anything because no matter what, the flow will just always change by 1. And so first we will set this visited array all to 0, and here we have to set everything to 400 instead of 200 because remember now we also think of the stalls as the same thing as cows, or you can think of it the other way. Think of the cows as the same as stalls, and we have to connect all of those. So here I'll also keep track of the parents of each node. And then here's the normal BFS. We first start at our original node, which is this 0, and this is the reason why I connected 0 to every one of the cows first. So we will be able to get all the cows. So we will first set this to visited, and then we will just use BFS to get all the other node. So we'll check all the nodes that are connected to the current node that we're searching for. And so we'll have to check if this current node is visited, or and if its capacity, if it has any capacity left. And so we have to search all the way from 1 to 405 because 400 we have to go all the way to the end of this node. So we have to count all the cows and all the stalls plus the ending node. And here, since there might be a few nodes that we don't actually use because n is not that big, or if m is not that big, then I can skip those numbers and skip right away to either count the stalls or count the final node. And so if we have more capacity in this edge from U to V, and we didn't visit V yet, then we will set the parent of this current V to U, which is at the edge, which is the node that we're searching for right now. And we'll also set V to visited and push this back into the queue. So this is just basically normal BFS. And then after we found the parents, we will get the minimum flow for this graph that we just made. So we will first set this current node to 405 because this is our ending node. And then we will get the parent of this current node, and we will set our minimum flow to the minimum of the current minimum flow and the capacity of this parent node to this current node. And so here we will get the minimum because we want to fill the pass as much as we can, but we don't want to overflow it. And so here we'll get the smallest capacity and fill all the edges that are in this pass with this capacity. And so after we've gotten the minimum, we can use this loop again. Using this while loop, we can get the parents again of this current node, which is starting at 405 again. And here we'll actually change the capacity of this edge. And so we will change the capacity of this normal edge from this parent node to the current node, and we will also add the capacity into our from this current node to the parent node. So this residual edge, we will use this to keep track of anything that we should undo, and this way this will undo everything. This will undo the paths that are not good. For example, if we cannot get an optimal flow out of this current path, so we will have this residual edge here to help us go back in case this isn't the path that we want. And at the end, you return this minimum flow. So then this minimum flow is the current flow that we have for this path, and we can add that into our answer, and then we will get the flow again. So first, the minimum here starts at 0. So if we cannot have any paths, so the minimum will always be 0, since the capacity will just be 0. You cannot have any negative numbers here. And so if the capacity is 0, then that means the path isn't available anymore. There are no more available paths, and that means we cannot add any more flows into this answer. So you can just stop this while loop, and finally you can print out the answer.